All right. What I'm going to do here is, in fact, go back a few slides and talk about that the RGCA, Reliability Growth Cause Analysis, because now is probably an ideal point. Let me go back to where we talked about that. This step here of understanding the parts and the risk the parts carry. This is in the workbook. And what we've got here, I'm just taking a simple, a part out of a machine. This particular part is the valve. This exhaust valve, I've just said, here's the technique we take. In this engine, some of these parts will do far more work than other parts. We're going to look for the parts where the stress is. The parts that are under stress are the ones that we're going to find. So I'm not going to worry too much about this issue here. That's simply bolted on there. The procedure needs to be written so that this is properly done, but this won't be under stress. That part will be under stress. Any moving parts, any parts that rotate, the pump internals are going to be under stress because they're being used. So I'm not going to do every single part because I can. I'm going to do the parts where the risk is to the machine. So out of 200 parts, there might be 24 in the end that I will actually analyse in some detail. So I've taken the exhaust as an example of what to do. We want to create the reliability block diagram of that situation. We want to create this thing into a process flow diagram, if I can get the right direction. So my exhaust valve is modelled as a process flow diagram, because that's how the machine is built. It's built as a whole series of parts, in this case 200 parts in some sort of reliability block diagram. So here I've got my exhaust valve, and what I want to ask is, for each of these activities, where can the stress come from for that part? And there's something to bring up a little bit. So I've taken the valve number. I've talked about where it is in the process. Heck, what's going on here? I need to reduce that a little bit. Come down here. Okay. Painful. All right, we're talking about a particular part. We're talking about the effect of that failure. If that exhaust valve fails, what's the effect on the engine? Will it impact the rest of the system? Now, if one item fails and it has no impact, then maybe that's okay, letting it break and because there's no knock-on consequence. But if there's a knock-on consequence from the failure and the engine's destroyed and the truck's out of service for 2 months and the truck's not making any money and there's business consequences, I need to understand, is there going to be a knock-on consequence? This particular diesel engine is actually the fire water pump in a fuel terminal. This is not the same diesel engine that could be used in a truck, but in this case, it's a fire water pump driver. So if this diesel engine does not work when it's needed, there's a risk of burning down this whole terminal. So this particular bit of kit is critical stuff, critical kit. So in this case, the tank terminal could burn down because the engine that's meant to pump the water through to put the fire out doesn't work. So if this engine was in a truck, the risk to the business is much less, possibly. If this is the business's only truck, then it might be a very high risk for the business because it's the only truck they've got. Though they could hire a truck in the meantime, which could be a strategy they put into place if need be. So yeah, we have to understand the scenario the equipment's in, because if this particular machine fails in this situation, they could lose their entire terminal and kill people as well, of course. Now we're going to ask what are the costs of doing this? This still needs to be a little bit smaller. If we do not do this, well, what sort of costs are involved? In this case, $500,000 or $500 million is the sort of cost involved. what money is saved by maintaining this thing properly. If to protect against this, we're going to have to strip this thing down on a regular basis. It's going to cost $25,000, which over the service life of this machine is $500 a year. So I can now justify what's the cost of caring for this properly versus the cost of not maintaining this properly and leading to a breakdown. So there's serious money here. There's not a lot of money to spend to protect the business against a real serious disaster. It may never happen. You know, this may never happen in the 50 years of this plant, but the risk is there. And that cost there of $500 million, $500 million is a very high risk to live with and do nothing about. So on my risk matrix, that would appear in the extreme risk zone. Now, that if I don't do anything, it's going to sit there, and all I'm hoping on is luck working my way. A very difficult way, an impossible way to run a business, counting on luck for things not to go wrong. So my risk matrix, I'm going to say, well, what do I do to get that risk down to acceptable levels? And it will be things like doing the regular maintenance required, ensuring the condition monitoring is done to make sure that the temperatures are properly controlled, make sure there's no blockage of the cooling system. You know, all the things that keep engines running properly, we've got to do those things. Not kid ourselves that we can get away with that. We've got to do it on purpose, proactively, to prevent the risk of this arising. So where does that risk come from? What sort of situations can cause our stress to occur on our particular part? Let's go down a bit further. So one of the failure modes will be the seats can be burnt. If the richness of the fuel is the wrong consistency, we'll actually burn the seats. And you'll hear of burnt seats in engines all the time. Very common problem. So we're going to prevent the seat burning. What's the frequency of that problem? Well, from industry, we can imagine some sort of scenario of in 1,000 hours of operation, the chance in 1,000 hours is certainly there. In 2,000 hours, the chance will increase. So the issue becomes, okay, what will it cost if that happens? I'm out for a month. On this critical pump that saves the plant from burning down, I can't be out for a month. This pump cannot fail. This engine cannot fail. What's the cost of supporting that and maintaining it? Not a lot of money to do that. Where can the degradation come from? As it's being used, this particular valve will be exposed to the risks. So it's during use of the machine that the valve is in danger of failing. What are we going to do to prevent that particular problem? Well, we can look at replacing the valves on a regular basis. We can ensure we do the maintenance required to protect the machine from failing. We may even want to mount some monitoring to check what the temperatures are during operation to make sure that it is not getting too hot. So we're going to put in place we're going to recognise the things that prevent the stress in the first place. Once we know what we need to do to stop that stress, we're going to build that into our maintenance procedures, into operating practices. And all that stems from the fact that this cause is a real possible cause. What other failures can occur? We can have timing errors. That valve can be burnt from timing errors of the ignition sequence in that engine. So what's the chance of that happening? If it does happen and we destroy the valve from mistiming, again, we're down for a month. The costs will be the rebuild of that motor, $25,000. We expect that to happen possibly once in 50 years. This terminal will have a life. Typically 50 years is a reasonable life for a fuel terminal. The chance is there that this might happen once. The reason it'll happen once is that we have not yet protected against it happening. So if I don't protect it, then the odds are there that we won't learn our mistake until we actually burn that fuel valve, until we burn that valve. So I'm expecting if we don't do nothing, then chance will go against us at least one time in 50 years, from which we will learn the mistake we have made by not protecting against it. So I've allowed for worst case one event, because we haven't protected against it, because it'll happen if we don't protect against it. And on down we go. For failure mode 2, what can we do to prevent failure mode 2? Now, none of these things are are going to be new. Now, the guys know timing's an issue. We know that valve getting hot will burn the valve and damage the seat. So we're not finding any new problems. What we're saying is these problems are real. They can happen. If they happen on this machine, it will be a high risk situation for the company. Because it's such a high risk, they cannot be allowed to happen. Then I must put into place the requirements so that it never happens. And the justification is, now we know what to do because each mode is recognised. Now I've got to write the procedures and operating practices to prevent these problems. So though everybody knows these are situations that arise, we have not yet put a cost, should they arise in this company, on this motor, in this scenario of a water pump in a fuel terminal. That's different scenario, different risks to this motor in a truck fleet of 100 trucks. Yeah? So what? This valve burns in that particular situation, so what?
What is that new matrix rating, likelihood 1, consequence 3?
Yeah.
What was the old one? I mean, what was the
previous one
current?
without doing that?
Yeah.
It's off the side, unfortunately. Yeah, we have got a column of the current risk. There's the numbers we get off our risk matrix. So it is there. That we want to have that process. Definitely want to have a before and after, because it's only the before and after comparison that justifies doing something.
So the likelihood went from 3 to 1.
Yes, and again, you would want to show that visually on your matrix. That's the whole. There's a lot of detail here, because I have to defend my recommendation to make the change. And I've got to be sure that in my head, I actually believe that this will make a benefit. And I show that thinking eventually in some sort of scale, some sort of risk matrix and some sort of dollar value, but I can't hold my hand on my heart and say, Mr. Manager, I believe I'm right and here's why, until I have a good analysis. So yeah, it's fairly demanding on the person doing the analysis to be very clear about the real situation. And if it's really a high risk possibility, then we have to recognise that and then come up with answers, proactive solutions. In the end, what will happen with this particular machine, we're going to have very good procedures on how to maintain it well and how to operate it well, and possibly condition monitoring. We're going to introduce, if necessary, some sure ways to make sure that the mixture, the lean richness of our fuel is correct. We're going to make sure that the timing is correct. Because if timing will burn the valve, if a lean mixture will burn the valve, they cannot be allowed to happen. So what will I do to prevent mistiming, to prevent wrong settings of the fuel-air ratio? Because they will happen. No? You see cars with black exhaust coming out of the exhaust pipe. That's the wrong air-fuel ratio. Someone set that or didn't bother correcting it properly. So these are things that happen on real machines. The trouble is it can't happen in this machine, in this situation, because it could lead to complete loss of the fuel terminal. And that's what we try and do.
You know, one thing that'll change that ratio that most people don't think about, I didn't think about it until it happened to me. If you have an engine that's been running for a while, a few years, you don't have to have anything wrong with the valves. The actual bolts that hold the head onto the engine can slightly loosen and suck air in from the side and change the ratio. Just slightly.
Yes, enough.
Change enough that it will turn on your check engine light.
So another failure mode, number 3, would be heads come loose.
And they can't just tighten the bolts. They, of course, have to take it off, replace the gasket.
Yeah. So if that is a possibility with an engine, a diesel engine, you wouldn't want to walk past that. May happen once in 100,000 engines, but that could be the 100,000th engine that it happens on. You don't know. That's what risk and chance is all about. This particular engine, you have no idea what will eventually happen. But 1 in 100,000 engines will have that very problem, and it could be this one. And is that an issue I'm willing to live with? At $500 million, no. For $500 million risk, I'd be happy to go there every 3 years, go and redo my head gasket every 5 years under controlled conditions.
Or I would tell them to get standby redundancy, get another engine.
In the real world, what happens in a fuel terminal, you've got to have two driving pumps. You've got to have two units to drive, electric one and a non-electric one. Because if I lose the power during a fire, electric motor stops, I've still got to fight the fire, and the diesel fires up. So in a fuel terminal, electric pump is your prime pump that fires up first because it's easier and quicker to do that, but your standby is the diesel.
You know, it'd be interesting to see a risk analysis of the nuclear reactor in Japan that shut down
After the
after
tidal
the
wave.
tsunami. Reactors are supposed to be loaded with backup diesel engines. None of them worked. There's got to be a reason for that.
Oh, yeah. Well, it'll be a business process failure of some sort, but the consequences are huge, yeah. So I guess, I don't want to be pulling teeth on this. The point is I don't want to do this for anything that's unimportant. So we want to find what parts are at risk of failure, what's the consequence if they do fail in this scenario situation, and if it's too big a consequence, are you going to live with it or not? Mr. Manager, tell me what to do. Can't live with it? Okay, well, here's my recommendation. Here are 15 things you need to do in your business process to protect against this, including every 5 years putting a new head gasket in, because I don't know if this is number one out of 100,000 motors. Or I can monitor. I could introduce some onboard monitoring to look for change in fuel-air ratio. Probably a monitor, you can install that on the side and it can begin monitoring continuously. And there are smart answers out there. The thing is to recognise where the risk is first, because if we can't see the risk, we'll do nothing about it.
Which is, it's easier to monitor for that in a car, so you ought to be able to do it anywhere. If that's one of the things that triggers the check engine light is a bad ratio.
Yeah. So we don't want to invent something new, you just want to recognise, hey, we've missed a really key dangerous issue here and we have to address it now and proactively forevermore. So that's reliability growth course analysis. If I fix these problems, I will create reliability. I'll actually prevent things going wrong. The part won't fail, the machine won't stop, the plant is safe, and the business doesn't lose any money.